All right, PowerPoint number 2 for, it should say Unit 12, Acids, Bases, and Salts for Ms. Howard's Chemistry class. And we still have the same things we're talking about. We're talking about the first 3 TEKs that you're required to know for the state of Texas. And we start off on the next set of the notes on Roman numeral number 2, definitions. There are 3 major definitions for acids and bases. You're going to be responsible for 2 of them. The first one was put out by Arrhenius, and Arrhenius said that, hey, when you have something in an aqueous or aqueous solution, you dissolve it in water, then if it's an acid, it's going to form hydronium ions, the hydrogen ions, in water. So that H3O plus and that H plus I told you about, they kind of use those interchangeably in many cases. So acids form the hydronium ions in water, H3O plus or H plus, whichever makes you happiest. So here we have HCl, and you put it in water, and you end up in that H from the HCl hooks up with the H2O, and so you end up with this H3O plus ion. So look at that funny looking molecule down there where you've got the O with 3 H's hooked to it. It's an ion. It's only going to form in an aqueous solution. And because it's an ion at H3O plus, and then you also have the Cl minus, that's why it allows it to run electricity through it. So it's an electrolyte in that form. Alright, so Arrhenius said an acid can be defined as a substance that yields hydrogen ions when dissolved in water. Again, we can, if you look at letter A here, it says hydrogen ions are also known as hydronium ions, and they're also written as H3O+. So it kind of depends on what you're looking at, whether or not you typically call them H+ ions or H3O+ ions. Hydrochloric acid, when it's dry, when it's not in water, is called hydrogen chloride gas. When it's dissolved in water, we say it's hydrochloric acid. So all of the hydrochloric acid that we have will be in liquid form. When it's dissolved in water, the hydrochloric acid breaks into ions. It's not an ionic compound. Remember, ionic compounds are made from a metal and a nonmetal, right? Metal left on the periodic table, nonmetal right on the periodic table. That's an ionic compound. They transfer electrons, and so they're naturally negative side, positive side. H is a gas. It's a nonmetal. Chlorine, a gas, nonmetal. So you've got 2 nonmetals that are bonded together, and they're sharing electrons. So when you take this covalently bonded stuff and you put it in water, it creates ions where none were before. So you get something that ionizes. It forms ions where you didn't have ions before. So it's kind of a little bit strange. Number 2, a base can be defined as a substance that yields hydroxide ions when dissolved in water. You should know that hydrogen ion or hydronium ion and the hydroxide ion. Stick those 2 ions in your brain and keep them there. Alright, so we have sodium hydroxide. It's like the quintessential base, sodium hydroxide, NaOH. Na is +1, the OH ion, the hydroxide ion is -1. Here we have Na is a metal, and then you have the polyatomic ion, the hydroxide ion. So here we have truly an ionic compound, a metal and some nonmetals. Not like the acid. KOH, potassium's a metal, the hydroxide ion, potassium hydroxide, barium hydroxide. Next one on here, you have some, again, definitions. Arrhenius said that in aqueous solution, acids produce hydronium ions, but bases form hydroxide ions. So here we have some pretty little pictures. You take the base, the standard NH3, and you put it in water, and it actually steals one of those H's from water. So you end up with an ion NH4+, and then there's the hydroxide ion all by itself. So you just created hydroxide ions in the water. Okay, so capital letter B on your notes. Bronsted-Lowry said that acids are proton donors. So basically what's going on is you had Arrhenius, and Arrhenius was really specific. He had the narrow definition, and he said, hey, if it produces hydrogen ions in water, it's an acid. If it produces hydroxide ions in water, it's a base. And a lot of times, especially with the bases, all you had to do was look at the formula, and if the formula has the OH ion in it, then you thought, oh yeah, that's a base. Bronsted-Lowry came by, and they kind of broadened the definition a bit. So it takes now into account those bases that are things like, baking soda. It's not quite so obvious that it has the OH minus ion in it. And they said acids are proton donors. And remember, a hydrogen atom has 1 proton and 1 electron. No neutrons in there for the most part. So if we are in a chemical reaction and we take off the electron, all that's left for that hydrogen atom is just this lonely little proton. So a hydrogen ion really is just a proton. And that's why they could pop up and say, oh yeah, acids are proton donors instead of just saying H donors. Acids are proton donors. Bases are proton acceptors. So we're bad. B-A-A-D. Bases, acceptors, acids, donors. B-A-A-D. So if you look at this one, we have HCl, and we put it in water, and we form Cl minus and H3O plus. Now, that H was taken off the HCl and it's hooked up with the water. We have the original acid, and water in this case is acting as a base. But when we talk about Bronsted-Lowry, what we end up having are conjugate acids and conjugate bases. Remember we talked about that word conjugate in class? Conjugate is kind of like the mate that goes along with it. So once we pull that hydrogen off of the HCl, what's left over? What's left over is the Cl minus. That's now a base, and we call it a conjugate base. If we take that H and we stick it on to the other one that's there, the base, in this case our water, we end up with an H3O plus ion, and it's now called the conjugate acid. Remember, acids can donate, so now that H3O plus can get rid of that H that just took away from the HCl. So we have these conjugate acids and conjugate bases. Number 3, acids and bases then come in pairs. You have a conjugate base, and it's the remainder of the original acid after it donates its proton or hydrogen ion. And then you have the conjugate acid, which is the particle that's formed when, hey, we took that H from the acid and we stuck it over here on this other one. So it's this new particle that's formed by gaining an H ion. Now, I'm going to throw another word in here at you. It's not on your notes, but it's the word indicators. And indicators are incredibly useful because indicators are chemicals. Usually they're weak acids or bases. And what they do is they change color when you change the pH of it. And oh my gosh, we have a book that's got like 50 of them listed easily. And so you can pick and choose which indicator you want. So you can say, hey, well, this is going to change at pH 2.39. And so we'll use that one. And this one's going to change color at pH 6.1. So you can pick and choose a lot of them. That's also what I talked to you about, the universal indicator. It has a whole bunch of those indicators together so that you can get a range of colors as you increase the pH. Okay, so again, we're talking about our definitions here. We have HNO3. What acid is that? It's got N, nitrogen. What acid? We take that acid and we put it in water, and that H pops off and hooks up with the water, and now we have the NO3 by itself. So we start out, in this case, our HNO3, our nitric acid is the acid, and that means the water, again, is acting like a base. And if we take the H off the acid, the HNO3, what's left over is the NO3 minus, and that's the conjugate base. If we take that H off the NO3 and we stick it onto the water, what's created over there on the right-hand side of the arrow is the conjugate acid. So we have a conjugate acid, H3O, and we have the conjugate base, NO3 minus. Okay, the reactants are usually the acid and the base, and the conjugates are usually the products. So reactants on the left, those are the original acid and base. Products on the right, that's the conjugate acid and the conjugate base. Now, in this, what you have right here, I've used water as both an acid. It was used as a base in the top reaction, and it's used as an acid in the bottom reaction. And when you have water where it can go either way, we say it's amphoteric, and it lives a double life, kind of like amphibians. Amphibians live a double life. They can live on the land, but they have to go back to water in order to reproduce. So that amphi means double or two. So that water being amphoteric means that it can go as both an acid and a base. It can go two ways. Acids and bases come in pairs then. You have number 4, amphoteric. It's a substance that can act as both an acid and a base, and that's water. That's huge for water. Okay, now the third definition, I'm going to throw this in here. The same guy that came up with the Lewis dot models, where you have the valence electrons, you have the symbol, and you put a dot for the valence electrons. So Na has 1 valence electron, so it's got 1 dot beside it to stand for that. The same guy who did that, he was just electron happy. He also came up with a definition for an acid and a base. So we had Arrhenius's definition, which was kind of small, and then we had Bronsted-Lowry, which is bigger. It includes more stuff, and it's practical. And then we have Lewis, who kind of gets a little bit carried away. In Lewis's world, everything is either an acid or a base, because he said, hey, acids accept electrons, and bases can donate the electrons. And you don't have to write that down on your notes. I'm just, putting it out there. Maybe it'll go on to the next slide. There we go. Okay, so here we have our little bullseye. So the Arrhenius model is kind of small. Definition is pretty small. And then we broaden it. Bronsted-Lowry broadened it to make it really practical. The Bronsted-Lowry definition is really the one that's probably most consistently used. And then Lewis, again, it's the most broad definition of what an acid and a base are. So here we have some of the gentlemen. Arrhenius came up and he said, hey, if it's an acid, it's going to produce hydrogen or hydronium ions, and a base is a hydroxide ion producer. Bronsted-Lowry, they were actually two guys. They were not working together. They were working separately and came up with the same idea. Acids are proton donors, bases are proton acceptors. And then we had Lewis, who's just electron happy.